Does anybody remember what time the seminar is today? I guess you got an email about it. It's like we're having seminars every day. 3 to 4? Is it Ravi? Rao. I love that name. Tata. So today we have yet another seminar that you should go to. It's Ravi Rao, who came all the way from India to speak here. I don't know if he was here already, but he's from the Tata Institute in Bombay. He's speaking today at 3 to 4, so you should come if you can. So I have a question, but maybe it's a stupid question. Do you guys want an extension for the project? So this is a stupid question. So I was supposed to make this trip to Colombia that made the scheduling very difficult for me to grade your stuff, but I'm not going anymore. So it's terrible news. but so let's make your project do the. Anything else you'd like? We're gonna make it not so the Monday after, right? So not this Tuesday, but Monday the 25th. Is that right? What day is today? 11th, so 25th. Wait, can I do that though? I mean, when is finals over? So that's really my question. The 28th. And I said 28th is a Friday. Thursday. No, then that's too little time. So let's make it do Friday then, which is Friday the 22nd. Yeah. Okay. All right. So. Okay, so we're talking about lattice ideals, right? And remember that one of the first things that I said in class is that one way to deal with an arbitrary ideal is to make it monomial in a way. And the way that we did that was by taking the initial ideal. So that's what I want to talk about next is talk about initial ideals of lattice ideals. So let me start with the example that we've talked about several times. The abelian group is Z2. The semigroup is generated by 3, 0, 1, 1, 0, 2. So maybe I'll draw it over here. This is 3, 0, 1, 1, and 0, 2. And then Q is everything that these guys generate, right? So I drew this picture several times. Now, what's the lattice? Well, we saw that one way of thinking about this lattice that is convenient is just to think of the lattice as telling us what linear combinations of these guys, what integer combinations of them are 0. And in this case, we said that, well, if you have 3 elements and they're of rank 2, every 2 of them are independent, the 3 of them are not, so there's a unique equation telling us that basically 6 times this one equals 2 times this one minus 3 times this one. And so basically the generator for this lattice is 2 minus 6, 3. 2 times this minus 6 times this plus 3 times this is 0. And the other integer combinations are all multiples of this one. Okay? And then given this, we made an ideal out of it by basically turning this into a polynomial statement where we put the positives on one side and the negatives on the other side. Right? So in this case, this thing looks like x squared z cubed minus y to the 6 0. Okay? And in this case, we said that this was generated by a unique guy. In general, the way we define this is that this is generated by x to the u minus x to the v, where u and v are vectors or natural numbers, and u minus v is in the lattice. Okay? And so this is the lattice of z linear relations on the generators of Q. So that's the data we start with, right? We're trying to analyze this ideal, and we're going to try to put together this procedure of taking the initial ideal of this guy. Okay? Now, I'm going to do this in a little bit of a different language than I did it earlier, and you'll see why in a second. Remember that if you want to take an initial ideal, you're supposed to start with an ordering of the terms. Okay? Now, what are the terms? Well, the terms are exactly the dots here, right? Each one of these dots is a monomial. And so when we did a term ordering, basically we just decided how to order these monomials. Example, well, we did this several times. But what I want to do now is that I'm going to take advantage of the geometry of this picture, and I'm going to introduce a term order by choosing a linear function here. Okay? So what I'm going to do is that I'm going to take something called a weight vector. And the way you should think about this is that, I mean, let's say that we're in the polynomial ring with n variables. Okay? So what I'm thinking is that W has n entries, and they're all positive, and I'm going to think of these entries as being weights on the different variables. Okay? So what I'm going to say is that a monomial, so the weight of a monomial, let's say x to the u, is saying what I just said. X1 has weight W1, X2 has weight W2, etc. So what you get here is, well, you have U1 X1s, and each one of them weighs W1. You have U2 X2s, and each one weighs W2. So it looks like this. Okay? So we'll do let's do an example of, let's do an example for this guy. And I think I'm not going to need anything except for, yeah. So let me just make these definitions. For this example, so that we see how this works. Okay. So in this example, we have, we can choose any weight or any weight vector. So let's say we chose, for example, the weight vector 1, 1, 1. Okay. So then I have to say what's the weight of x squared z cubed. Well, I'm saying that x has weight Maybe I should make this a little bit more interesting so that you can tell what's happening. 1, 3, 2. So what I'm saying is that x has weight 1, right? And there's 2 of them, so I get 1. We get more interesting. I think we might get confused here. So let's use 5, 7, and 8. Okay. So now x has weight 5, and there's 2 of them, so I get weight 5 times 2 for the x's. There are no y's, and then the z's weigh 8, so I get 8 times 3 equals 24 plus 10, 34. Okay? So that's the weight of that monomial. And let's take the weight of the other monomial that I see here. The weight of y to the 6th is 6 times 7 equals 42. Okay? And what I'm going to do is that I'm going to let this weight decide which one of these 2 monomials is bigger. Okay? Because that's what I need to do. I need to organize my monomials so that I can choose what the bigger ones are. And I'm going to let this be the deciding factor. So what I say is that if I have a polynomial in n variables, then I'm going to take the initial polynomial, and this thing is the sum of the W maximal terms in P. Okay? So for example, when I take the initial term with respect to the weight vector of 5, 7, 8 of this thing, then what I'm supposed to do is say, well, this guy has weight 34, this guy has weight 42, so this is the heavy one, and I get minus y to the 6th. Question?
Are these weight vectors a complete order?
Not necessarily. So I want to do an example of that next, actually. But is it clear how I'm defining this initial polynomial? The sum of the W maximum terms. So here this has weight 34, this has weight 42, and so I keep only the one of weight 42. Okay. But let's do another example. So I can take the initial polynomial with respect to the vector 3, 3, 2. Okay. So then this thing has weight 3 times 2 plus 3 times 2. So that's 12. Right? And then y to the 6th has weight. Oh, I did this wrong, didn't I? No, I meant to do this, sorry. 3, 2, 2. Okay? So with respect to the vector 3, 2, 2, this guy has weight 12, and y to the 6th has weight 6 times 2, which is also 12. Okay? And this proves Steve's point that actually this might not be a total order, and if there happens to be a tie, then you have to keep both guys. Okay? So you'll notice that when if you rewind the video, you'll see that I said initial polynomial, where before I used to say initial monomial. And the reason I did that is because now this might not be a monomial. Okay? Now, if I have an ideal, for an ideal I say that the initial ideal is the one generated by the initial polynomials of polynomials in the ideal. Okay? And basically, what I want to do is now do the theory of Grosvenor basis with respect to this slightly different definition of initial. But actually, the way that I want to do this is that I generally want to do this for W's that are generic, in the sense that this didn't happen. Okay? Generally, if you want this theory to work easily, you're not going to choose one of these guys. You're going to choose one of these guys, which is what we call a generic W. Okay? So I'm going to say W is generic for I if this thing is a monomial ideal. Okay. And as we've seen in the several times that we've used the word generic, the point is that most W's have this property. And I think if you want to hear more about this, I think Deborah and Thomas can explain to you a lot about this. So the point is basically that the W's that are not generic are along some lower dimensional things in the space of W's, right? W lives in Rn, and most of W works except for some kind of lines and planes and things like this. But most W's are generic. It's actually really pretty. So if you want to understand how this works, that's the theory of the Grosvenor cone and things like this. Okay. So what else should I define? Well, just the same thing it says before. We'll say that a Grosvenor basis. So let's say that a set G, a subset of an ideal, is a Grosvenor basis. This is too many shortenings, but Grosvenor basis with respect to W if the usual thing holds, right? The initial terms of G already generate the ideal, the initial ideal. Okay? So same definition as before. As before, it's important which W you choose. If you choose a different W, then that might or might not change the property of being a Grosvenor basis. And again, for each generic W, there is a unique reduced Grosvenor basis. So same definition of reduced Grosvenor basis works. Reduced Grosvenor basis with respect to W is still unique, as long as W is generic. Okay. So this is kind of the general setup. And you see, for example, according to, well, maybe let me prove something here. So it's a proposition. We defined isobel to be generated by these things, right? X to the u minus x to the v, such that u and v are vectors of natural numbers, and u minus v is in the lattice. Okay, those are the generators of isobel by definition. What I want to prove is that actually, if I consider these guys, they're a Grosvenor basis, no matter what W you chose. Okay? So this set is a Grosvenor basis for isobel with respect to any generic W. which when you think about it is kind of amazing because we used to do things for a single W, and already finding a Grobner basis was kind of tricky. But we're saying that this works for any W that you choose. Of course, the trade-off is that this set is huge. But how do you prove this? Well, what we're going to do is this. You guys remember how you prove that something is a Grobner basis? It's been a while since we've done this. Where we take these S polynomials, right? So for every pair of generators, we take the S polynomial. So let's take two of these guys. Okay, and we're supposed to form this S polynomial, and we're supposed to show that it's 0 mod that set. Okay. So there's two ways of doing this. And you can do it kind of purely algebraically, or you can do it with pictures. And I'm going to do both. Okay. So I want to think of x to the u minus x to the v as something like, maybe I'll draw that picture over here. U and v are vectors, right? And so let's think of x to the u minus x to the v as this thing. Okay. And maybe I'll think of x to the u prime minus x to the v prime as this thing. And so the point is that this thing is in, u minus v are vectors, so this is a vector in L, and u prime minus v prime is a vector in L also. Okay. Now, W chose a maximal term in each one of these monomials, and depending on the W, it might be u or it might be v. But for simplicity, let's assume that it's this one. It doesn't really matter. Okay? So let's say that W chose these guys to be the W maximals. Okay? So then what are we supposed to do? We're supposed to, remember, we're supposed to find a multiple of x to the u and x to the u prime so that we can cancel, and that is the LCM. Okay? Now, where do I see the LCM in this picture? Is it clear what this picture is? This is supposed to be a picture of n to the n, which is where u and v and u prime and v prime live. So, for example, this might be, if I had x squared z cubed minus y to the 6th, then this would be 2, 0, 3, and this would be 0, 0, 6. Okay? So now I need to find the LCM, but finding the LCM in this picture is very easy, right? We did this with staircases many times. That LCM is exactly right here. So what I do is that if I call this vector A and this vector B, then what I want to do is, and then of course, this is u plus A, which is equal to u prime plus B. Okay. So the way this polynomial works, I multiply the first guy by x to the A. Then I multiply the second guy by x to the B. And the point of doing that is that this guy and this guy are going to cancel. But you see, when I multiply this guy by x to the A, what I'm doing is kind of shifting this thing over here. I'm shifting this thing over here. And when I multiply this guy by x to the B, what I'm doing is that I'm shifting this guy over here. No. Sorry. So this is x to the A times x to the b, and I want x to the b times x to the b prime, so what I want is, yeah, sorry, this guy. So in my picture, this is going to be v plus a, and this thing is going to be v prime plus b. Okay. Now let me do the algebra. What I get is x to the b times x to the v prime minus x to the v x to the b. Okay. So I compute the S polynomial of these two guys, and what I get is this thing. Okay? And now I need to reduce that mod my set, which I want to be a Grosvenor basis. Okay? But what I claim is that this thing is in this set. Now it has the chance to be because it's a binomial, right? But I also claim that this binomial is in this set. How do I check that? Well, I don't know, let's call this set G. So to check that this guy is in G, what I need to check is that when I subtract the exponents, this thing should be in L. Okay? But this is easiest to see in the picture, because this vector is this vector right here. And so I've made a triangle where two of the vectors are in L. And that means that the third vector has to be in L, because the third vector is the sum of the other two. And that's the end of the story. Why? Because remember, L is a lattice. So if you add two things in a lattice, you stay in the lattice. So if this purple thing is in the lattice, and this purple thing is in the lattice, then the orange thing has to be in the lattice. So that's the proof. Now this is a very comforting theorem, actually, because if you think about this, well, maybe let's talk about the comfort of this theorem in an example. And this is the example that I wanted to draw right here. But maybe before I draw that example, I'll just make one more definition. So if W is generic, then the initial ideal of U of I is monomial. Right? Like in this case, it's y to the sixth. It's generated by y to the sixth. And what I want to do is I want to take the radical of this thing. Okay? Sorry, just tying my shoe. I'm not doing. Guess I just disappeared. So this thing is a monomial ideal, and I'm going to take the radical. So I defined the radical for you last time. The radical consists of I'll write it out. So the radical of this consists of the polynomials such that p to the k is in the initial ideal for some k. Okay? So for example, the radical of the initial ideal with respect to 5, 7, 8 of the guy we started with is, well, first I take the initial ideal and I see that the initial ideal is generated by y to the sixth. Okay? And then I take the radical. And for monomial ideals, what you're doing is just chopping off the exponents. Okay? If y to the 6 is in the ideal, then y is in the radical. If you had that x squared z cubed was in the ideal, then xz would be in the radical. Okay? So you can just think of this as that you're just dropping the exponents in this monomial ideal. Okay? Now the reason for doing that is that that takes a monomial ideal and makes it into a square-free monomial ideal. Okay? And we like those very much because those guys are the Stanley-Reasoner ring of somebody. So this thing is the Stanley-Reasoner of some simplicial complex which we're going to call the initial, we're going to denote it like this, delta sub w of I, and we call it the initial complex of I with respect to w. Okay. Now, the problem is that in this example that we have, there's nothing going on, because what did I do? I started with my ideal, right? And my ideal was generated by x squared z cubed minus y to the 6. Okay? I took the initial ideal, and then I took the radical, and I just got the single polynomial y. Okay? And I'm saying that this ideal is the Stanley-Reasoner ring of something, but that's a really boring simplicial complex that the Stanley-Reasoner ring is just generated by y. Okay? So what I want to do is I want to now give you a more interesting example, and then we'll see how these definitions work. Because I think here we just don't see anything. Okay? Yep. This k? No, it's a number. For some k natural number. Maybe let's compare two things. Let's consider an initial form. This weight vector gave me the initial term y to the 6th. Okay? Now let me consider a different example. For example, let's consider the initial vector 1, 0, 0. With respect to 1, 0, 0, what is the initial term? Well, now here, this thing has weight 2 plus 0 plus 0, and this thing has weight 0. So the initial term in this case is x squared z cubed. Okay? So these are the initial ideals for two particular w's. In the first case, I got y to the 6th. In the second case, I got x squared z cubed. I'm going to switch my parentheses to brackets, and that needs an explanation. I'm doing something slightly non-trivial, which is just saying that if I want the initial ideal, then what do? Well, I take the generator and take the initial polynomial. And then I take the ideal of that. So what this says is that the initial ideal with respect to this weight is this one, and the initial ideal with respect to this weight is this one. And now I need to take the radicals of these two things. Okay? So what are the radicals? Here you just drop the exponent, and you get, and you can drop the constant because the constant doesn't really matter as far as generating, right? So here you get y, and here you drop the exponents and you get x, z. Why is that? Because if you raise this thing to the 6th power, you're going to land there. And if you raise this to the 3rd power, you're going to land there. But for example, if you just had x, you could raise it to whatever power, and it's never going to be a multiple of x squared z cubed. Okay? So that's why taking the radical is basically just forgetting the exponents here. Okay? And now what I'm saying is I want these things to be Stanley-Reasoner rings of a simplicial complex. I know I can do that because I have this thing between square-free monomial ideals and simplicial complexes. It's a correspondence. Okay? And if you have to remind yourself how it works. The generators that I put in my square-free monomial ideals are the non-faces of the simplicial complex. Okay? So what's the simplicial complex that I get here? Well, it looks like this because xz is a non-face. Okay. X is a face, so it's not a generator. Z is a face, so it's not a generator. Xz is a non-face, and so it is a generator. Where's y? Well, is y a face? Y is not a generator. Let's see, what do I want to say here? Let's do this for a bigger example, and you'll see that it makes more sense there. Okay? I guess the thing is that I'm not really telling you whether y is in the ground set or not here. So let me tell you in a second because I have to think about it. Okay. But let's do an interesting example, which is this example right here. So remember that we said last time that if you take any cone in Z2, then, so here's a cone in Z2, right? C. Okay. It's a cone in R2, I'm sorry. So when I say the cone, I mean all of this stuff. It's in R2, and it's a rational cone. And the reason it's a rational cone is that if you look at the rays generating it, here's a lattice point. This is 1, 2. And I have to look a little bit harder for a lattice point here, but it's 1, 2, 3, 4, 5, 6, 7, 2. Okay. Maybe I'll put these here. 7, 2, and 1, 2. And we proved last time that if you look at all the lattice points inside this cone, we're going to get a semigroup. Okay? And so let's do that now. Let's consider all the lattice points that are inside here. So this one, all of these guys. Now, by definition, this is a saturated semigroup. Because remember that what it means to be saturated is that basically everything in your cone is in the semigroup. A saturated semigroup is exactly one that arises in this way. And we said that saturated semigroups have a unique minimal generating set, which is called the Hilbert basis. Okay? So I start with a cone. Now, what's the Hilbert basis? What are the minimal generating guys? Well, what I'm going to do is I'm going to give you a recipe of how this works in general. What you're going to do is take all of the points in your cone except for the origin, and take the convex hull of that stuff. Okay? So, what's the convex hull of all of them except for this one? So this guy's not there, so the convex hull looks like I have to go here, then here, then where do I go? Over here, right? And then there's points over here. Along this line, you keep having points. Along this line, you keep having points. Okay. So do we agree that the green thing that I drew is the convex hull? Let's see, I want to call this P sub C. P sub C. This is the convex hull so let me define Q to be the semigroup of lattice points in here. Okay, semigroup. And then P sub C is the convex hull of all the points in Q minus the origin. Okay. So this is C is a cone in R2, that's right. And I'm intersecting it with Z2. Okay. And then I take the convex hull, and that's all this green stuff. Okay. It's all of this stuff. Now, this thing is going to be a polyhedron. And it's always going to look like this. I mean, if you think about what a cone looks like, a pointed cone looks like, in R2, it just has two rays. You just get to choose what the two rays are. So it's always going to look like you have an infinite segment, an infinite ray going that way, then some finite things here, and then an infinite ray going over here. Okay? And if you look at the vertices of this guy, that's going to be the Hilbert basis. So this is a fact. The vertices of this thing are the Hilbert basis of the semigroup. Remember, Hilbert basis means minimal generating set. Okay. So in this case, it's this guy. I should say it's not the vertices of PC only, because you also need to throw in guys that like this one, that it's not a vertex, but it is on the bounded part. Okay. So what I should say is not the vertices, but the points on the bounded segments of PC. The lattice points on bounded edges of PC. Okay. So in this case, this is my Hilbert basis, 5 guys. Okay. So let's write them out. This is 1, 1, 2, 1. So now I want to take this guy and write the lattice ideal. And the lattice ideal tells me what are the relations between those generators. Okay? So let me write out what it looks like in this case, and then we'll talk about why it looks like this. For example, I have a generator like this one. And what this means is that if I call these guys A1, A2, A3, A4, and A5, then, for example, the reason I have the isobel in there is that if you add up A1 and A3, you're going to get 3 times A2. So this is the polynomial version of that. 1 A1 plus 1 A3 gives you 3 A2s. Then, for example, what is 1 A2 and 1 A4? You're going to get exactly 2 A3s. What is 1 A3 and 1 A5? It's hard to see in the picture, but it's easier to see in the equations. 2, 1 plus 7, 2 is 9, 3, which is 3 times A4. Okay. So these are some of the generators, and then I have other ones that look like this. X1, x4 minus x2 squared x3. X2, x5 minus x3, x4 squared. X1, x5 minus x3 to the 4th. So each one of these things gives you a linear relation between the AIs. Okay. And you can easily check that each one of these things is a relation. And what I want to justify to you is that that's it. This is a generating set for the ideal. Okay? And I'm going to do it like this. So for now, let's leave this open to the possibility of having more generators. Okay? Now, really what we want to do is an example of this initial ideal business. So what is the initial ideal with respect to the vector 1, 10, 100, 1,000, 10,000. So, of course, the point is that I'm giving my variables these weights, and what I want is that 2 is much heavier than 1, 3 is much heavier than 2, 4 is much heavier than 3, etc. So the reason I want to do that is because, for example, I want this to win over this, because whenever you have an x3, that's going to be bigger than having an x2. This has weight 1,001, and it has weight, 101, and this has weight 30. This guy is heavier than this one because it has an x4. This guy is heavier than this one because it has an x5. This guy is heavier than this one because it has an x4. This guy, this guy. Okay. So at the very least, the initial ideal contains these guys. x1, x3, x2, x4, x3, x5, x1, x4, x2, x5, x1, x5. Okay. And, well, as we said, that we should be open to having more things. Now, let's say that for now you believe me that that's it. There aren't any more. Okay? If there aren't any more, then this is the initial ideal, and now we want the initial complex. So first, if you want to take the radical, then you get the same thing, right? Because there's no powers here to erase. Okay? And so what we're looking for now is a simplicial complex that has this Stanley-Reasoner ideal. Okay? So what do we do? What we do is that we put down a vertex for each variable that we see. Okay? And then these guys are the minimal non-faces. Okay? So I don't put an edge between x1 and x3 because this is a generator here. I don't put an edge between x2 and x4, etc. But for example, I do put an edge between x1 and x2 because you don't see that here. And 1b2 and x2 and x3, between x3 and x4, between x4 and x5. And this answers the question that you had earlier, Andrew. Basically, if a single variable appears, like it does in this case, that means that you're supposed to put y in the ground set, but not as a phase. And if it doesn't appear at all, then you don't even put it in the ground set. So this is an example of the initial complex. Okay. Now, why am I saying that there aren't any more things? Well, what else could live here? The only way that you could add things to this is if you had, for example, something like x1, x2. Could you have something like x1, x2 here? Well, if you did, it would be because here you had something like this. But I claim that you can't possibly have this, and why is the reason? The reason is that this in the picture would say that that A1 plus A2, right, which is over here, A1 plus A2 lives in this cone, would have to be expressible in terms of things that don't have x2s. They have to be smaller. Okay? In this case, I could only have x1. And there's no way that I can get that x1 plus x2 is a multiple of x1. A more interesting example is if I had x4, x5, or like let's say x3, x4. Could I have this? Well, I can't, because if I had a relation like x3, x4 minus something over here, what would that mean in this picture? That would mean that I managed to